This is not even wrong podcast. It's November 4th, 2023. This is Crimdelco. It's a Saturday, no updates. For the year, we are up 90.6%. The market's up 13.5%. We're outperforming by 77.1%. So the week from 10/3/30 to 11/3. The first event I want to mention is really interesting. It's a PhD student from the university, from Georgia Tech. And she is part of the sort of material science, nanomanufacturing, computer architecture group. The group there is very similar to Onur Mutlu. They're talking about, for example, problems of data-centric compute, problems of faster processors, nanotechnology to increase the speed of processors. So things along those lines. And I think in this particular seminar, the lady was introducing adaptive oxides as a possibility for in-memory compute. This is physics-based in-memory compute. Active oxides such as titanium oxide are state-dependent oxides. In other words, you can store a state in there and then do a computation on the substrate and change the state. And this can be used for let's say weight accumulation in neural networks. That's why it's called brain-inspired learning, because as far as we know, our brain is able to do massive computations with very little watt consumption, and that is because we do a lot of compute and memory together. So this what's called Memsistors, also this idea in material science and electrical engineering, which is the combination of memory and transistors, or in other words, you have a device that can be used as a logic device and also as a memory device at the same time. So this is physics-based in memory compute, and Fabia Farlin-Athena, the PhD student from Georgia Tech, was presenting this. The seminar was hosted by Philip Wong. Now, Philip Wong is an interesting person. He himself is Chief Science Officer of Taiwan Semiconductor. He works on carbon nanotubes, amongst other things. And what he's trying to do is build really two big picture things. One is he wants to build faster, smaller transistors. And the other is he wants to build data-centric, memory-centric architectures where data doesn't have to move back and forth. This is really along the lines of Onur Mutlu, and that's why I was really excited about this. So in his website, for example, he has this quote: 21st century information technology must process, understand, classify, and organize vast amounts of data in real time. 21st century applications will be dominated by data-centric computing operating in terabytes of active data with little locality. At the same time, massive redundant sensor arrays sampling the world around us will give humans the perception of additional senses, blurring the boundary between biological, physical, and cyber worlds. So, and he goes on and on. So I think this is definitely akin of what Onur Mutlu is doing. So which shows me that this research in data-centric compute is a big deal in computer architecture. That's probably also why they brought Onur Mutlu over. Wong has in particular worked on carbon nanotubes as used in transistor technology. Carbon nanotubes have a couple of properties which are really good. They're very small. They have very good electric conductivity. In other words, you don't need a strong signal to activate a carbon nanotube. So you can do something along the lines what the lady did at Berkeley when she did mechanical switches. You know, one of the problems in transistor technology is that you need quite a bit of voltage. I mean, of course, very little voltage compared to what we're used to in let's say, high voltage transmission and things like that. But nevertheless, the less voltage you have to use to activate a switch or to do something in terms of logic, the less power you need, of course, when you have, 20 gigahertz type clock cycles, maybe at some point, then every little bit of less voltage makes a big difference. So Wong has written a book about this. He has also written papers about it. I don't want to go into details here. This wasn't part of the presentation. I guess to summarize, this seminar was really interesting to see what PhDs are doing. This particular lady, she has a background in material science, and now she's doing a PhD in something that I think is very physical, but her job is really to work with these Memsistors, these adaptive oxides, which are a part of, or which are used to build Memsistors. So Memsistor is more of a global class of things that can be used as memory and resistors. Memory and transistors. I'm not sure if the sister comes from resistance or transistor. It doesn't matter. But think about it this way. You have a physics-based in-memory compute here. And what's really interesting is that the way she works, for example, she has to build very high electric conductivity with very low thermal conductivity, which of course is incredibly difficult. I mean, if we had technologies that can do this, let's say for cars and things like that, then we would have much more powerful cars. The problem is always the same, right? You have this, you want to have high electric activation and very little heat dissipation. In other words, you want to have very efficient devices. So she's working on materials, on doping technologies, on things along those lines that can enhance that. So I would say, again, this is a very interesting seminar from that perspective. Another interesting quote on Wong's website is, I'm quoting, "Our research on memory devices broadly," actually, no, I want to go a little bit further. "I started doing research on memory devices around 2003. Research on memory had been rather predictable for many years until recently." And then he goes on and he talks about how the smaller and smaller scale made memory more and more difficult. This is very much along the lines of Onur Mutlu. And then he says, "Our research on memory devices broadly covers phase change memory, metal oxide resistive switching memory, RRAM." So that is what this lady was presenting, and then others. And we explore the use of various materials, device structures to achieve desired characteristics. So we're still in sort of material science, physics, and electrical engineering phase. And it's just interesting to see how this combination of sciences and knowledge hopefully will yield results, and also an inspiration for doing a PhD in this type of environment. The next meeting I want to talk about was organized by the Stanford Intelligent System Lab, CISL. Peng Wei from, I believe, George Washington University, yes, talking about coordinated learning-based autonomy for urban air mobility. So the problem here is you have flying agents, but this could also be self-driving cars on the ground. It doesn't matter. It's the same problem. You have agents driving around, flying around, and how can you coordinate so they don't collide? So Wei is a sort of air traffic control type person. His background is in control theory. So, he's along the lines of, how can we, manage a system, induce it with signals so it performs a certain way. It does certain things that we set as goals. And not surprisingly, he's now using reinforcement learning methods, because that is really the flavor du jour in these types of problems. You have agents and they interact with each other, and you can infer from those interactions certain processes that could end up in an optimal design of a system where you don't have, let's say, even central planning. So these are still philosophical questions. I think Wei himself, a pretty dynamic, interesting person. I spoke with him afterwards, and I asked him one specific question, which was, can you get into a situation where they checkmate each other? And he said, that's a good question. We should think about it. I met a person in a later seminar at CARS, the Center for Automotive Research at Stanford, where they actually did a similar problem, where they looked at similar problem on the reinforcement learning side. That problem there was not about traffic management per se. It was more about deployment of ride-sharing cars and using reinforcement learning to optimize that. So I think in general what's going on here, and this is obviously pretty close to home now since I'm doing the reinforcement learning course by Sergey Levin. Look, you have a problem, that is, you have multiple agents that interact with each other. You have a certain goal, which is, of course, in the case of Peng Wei and the sort of flying agent type problem, you don't want collisions. They all have to go from A to B. They all have to reach their destinations. They all don't want to waste energy. They all need to, get somewhere at a certain time. And what you don't want is collisions. So you could use reinforcement learning to do that. I think that's really the gist of this paper. Wei is talking about learning-based methods, and I think one of the things that I kind of noticed that he said he gave a class on reinforcement learning, at the university. And, this already shows you how dangerous academia can be. This is a person from sort of control theory. So he's in line with, let's say, Jitendra Malik on that front. Like, his background is there. And quite frankly, given his background and given his work, he spent a lot of time working with the TAA, which is the sort of the administration here in the US, organizing air travel, making sure it's safe. So why would somebody like that have an insight into teaching any kind of machine learning class or in reinforcement learning? Now, I think math is certainly an important ingredient for a successful reinforcement learning career, and maybe there's a nice transfer learning happening there. But I would be a little bit skeptical if I was a student of his. But nevertheless, I mean, it's of course laudable that he's transitioning and learning about these things. I'm just a little bit skeptical about if he should be giving a course. But then, the best way to learn things is to teach them. Next seminar I want to talk about is Huimin Zhao. He is, interestingly enough, we're just talking about Chinese people here, and that's just a big prevalent situation that most of the scholars that I'm meeting here at Stanford are from Chinese origin, and I just want to leave it at that. So Huimin Zhao, he actually is at Illinois at Urbana-Champaign. Now his idea is synthetic biology aims to improve novel biological systems using engineering principle, which has broad applications in medical, chemical, food, and agricultural industries. Now, thanks to advances in rapid DNA sequencing and synthesis, genome editing, artificial intelligence, we can create a lab that can basically automate a lot of the biological functions. So this is similar to Syntago in a sense. I think the most important thing of a project like this, in my opinion, is that you can reproduce biology. If you had a systemized, standardized process, workflow, robotized everything, you could have a situation where you actually have really well reproducible biological systems, biological production. That's one of the things. Of course, you could also have low-cost production and things along those lines, but that's not even the main thing. I think really the idea here of reproducibility, in my opinion, is really the biggest upside. Zhao mentions 4 big, ideas that he sort of wants to achieve here, or goals. So big automata, self-driving biofoundry for pathway engineering and protein engineering. Second, an AI tool for enzyme engineering. Third, an AI tool for enzyme function prediction. And fourth, an engineered genome editing system with high efficiency and specificity. So what is he doing here? So he wants to create enzymes and also predict how they function. So these things can all be automated. There is a lot of menial work, a lot of repetitive menial work that, in my opinion, is automatable, that robots could do it. And this also poses a really interesting robots problem, right? How to do, let's say, fine-tuned, dexterity, intense biological functions. So I'm not sure if the robotics community is working on these problems, but this is certainly something that, grasping things along those lines. I'm going to attend remotely, albeit, but still I'm going to attend Coral 2023 Atlanta next week. It's in Atlanta. And I'm going to be attending again remotely, so just read the papers, listen to the keynotes, that sort of thing. And I think I'm going to be looking for these types of applications. I think automating robotics and automating biologics through robots, to me, is actually a really big application space, because we have a problem in biosciences of reproducibility, high cost, all those things. And I think robotics could save the day here. Zhao also worked on DNA storage, although almost 10 years ago. He also mentioned actually Twist Bioscience in the talk, because he's buying synthetic DNA from them. And it's just interesting how the circle closes. We obviously were investors in Twist, amongst others, because of DNA storage. There's a paper that summarizes sort of the up-to-date technologies by 2015. I read through, it's not too interesting. I think in the last 8-9 years, this technology has advanced massively. So I think it would be worth doing a rewrite on that front. Next is the physics colloquium. I really like that colloquium because even though it's pretty high level and often way above my head, I think it gives you a good sense for what physics professionals are doing. In this case, Chris Laumann from Boston University was presenting work on quantum spin ice. Quantum spin ice is a particular configuration that magnetic materials can have, which is akin to water ice. Water ice has a certain setup of proteins. The water molecules, they set up in certain ways that create water ice, which makes it lighter than liquid water. Things also. So you have this really weird, unusual situation where you have a dense solid which is lighter than the liquid of the same material. So quantum spin ice has, of course, very different properties, but the idea is the same. That's why it's called ice. And in this case, it's not the protons, but the actual spins of the material, of the molecules that have a certain, it's two in, two out type characteristics. So what's interesting here is not necessarily, at least for me, the actual results. I'm not that deep into things like quantum spin ice, but just the work itself. Chris presents measurements, theoretical measurements, and also some practical experiments in terms of simulation of how this quantum spin ice should be behaving, what the properties are, what the conductivity is, the magnetism, entanglement, things along those lines. Again, was a little bit over my head. He also wasn't, I would say, not a very good presenter. So in that sense, he was a bit snidey. He constantly made remarks. He also got, I think, chastised by one of the older participants of the colloquium. He asked a question, and then Chris gave another snidey, sort of humoristic remark. The question was, how many parameters do you use in your simulation when you're studying this particular phenomenon? And then the answer was, well, how many do you want? And then the person got a little bit angry. The person that asked the question said, this wasn't a stupid question. Can you please answer the question? And then Chris sort of answered the question. He said, look, I think this particular parameter that he was measuring, and I forgot exactly what it was, but this particular parameter is independent of the parameters that I use to measure it, something along those lines. And again, he's certainly a very accomplished physicist, professor, undergrad from Princeton, but the personality is a little bit on the snidey side. Next is a lecture by a postdoc who actually researches the sun, and I thought this was really, really interesting because this was first, you got some knowledge about the actual sun, but more importantly also, you got a really good sense for what solar astrophysics is all about. So this person, his name is Sushant Mahayan. He is a postdoc. He got his PhD, I believe, University of Virginia, University of Georgia. Now he studies the sun, and what does that actually mean? So you look at, you have these large telescopes, you look at the sun, and you try to measure stuff. For example, they use sound waves and sound wave technology and detection to see what might be going on in certain areas of within the sun. Without going too much into detail of what that actually means, some of the goals are, one of the most important goal is to predict solar flares. So he said that there is something like solar weather or space weather. Space weather is very similar to our weather on Earth. We have situations in space that create turbulences, sometimes radioactive stuff, electromagnetic waves, things along those lines that can influence, let's say, air travel on Earth or space travel on Mars. So it's good to be able to predict these things, and the solar flares are one of those important things that we try to predict. So we try to predict when they happen. We try to predict the frequency of when they're happening, and also location-wise, so we can then help space travel, have a better sense for where they're going, and also avoid problems, radiation exposure, things along those lines. So the presenter presented sort of first a bottoms-up approach. Okay, what's going on in the sun? In the middle, we have the plasma, the energy creation of our universe, the fusion of hydrogen atoms into helium. Then we have, that's about 25% of the core. Then we have the sort of 60% between the outer crust and the plasma is just radiation, and I guess I'm not quite sure, maybe gaseous form. I would say it's gaseous form. Actually, yeah, the Earth is, excuse me, the sun is mainly a gaseous sort of ball. And then we have the crust, which has a little bit different composition again. And there's a lot of stuff going on. There is magnetic forces going on. There is the dynamics of the rotation of the sun, which, because it's gases, have different vectors affecting different areas of the sun. So there's a lot of that. Some open questions: what creates magnetic fields in the sun? Another is, why is the sun actually much hotter, sort of very close to the surface than on the crust itself? What's really interesting is also how they measure these things. That in itself is just amazing. There's supercomputers at work, there's machine learning algorithms at work, because what you're doing here is really find the signal in the noise, analyze the data, and therefore it just showed that solar astrophysics has a big sort of transfer knowledge component to its field. Next is a seminar on operations management. This is actually my first visit to the GSP, sort of, back to the roots, if you will, as a former GSP grad, although not the GSP of Stanford, but GSP of Chicago. However, the professor that came is from Chicago, today called the Booth School of Business. And he was talking about flexible resource planning. So if you have demand coming in, and you have resources supplying that demand, how can you structure a network that is flexible enough to produce demand N at, node N1, excuse me, the demand N1 can be produced at node S1 or S2 or S3. How many connections do you need? How much flexibility do you want? Those are the kinds of questions that Yuan Zhong is asking. He himself is a math major, background with math and operations management, operations research, applied statistics. I think, again, interesting here is not just the results per se. Those are business problems, real business problems that we at Orange Capital Partners actually do think about. Let's say, how should Tesla, procure their supply chain? How much flexibility do they need? The more flexibility, the better. The more adaptive you are, the better, of course. And Yuan Zhong is solving those types of problems with analytical tools. Now, in general, I would say there's a lot of riffraff about nothing, but then when you really analyze it to the core, you do find the problems a little bit more complex than they might think in the first place. For example, if you have 20 factories around the United States, how do you want to cluster them? And more importantly, how do you want to connect them? Now, I asked him that question afterwards, which is, why isn't everything just a network problem? In a sense that you shouldn't have any sparse capacity, any locality. You should just produce wherever you have capacity and then deliver wherever the demand is, and neglect transportation costs. You can do that maybe with data. You can do that with certain types of goods, but mostly, he said, of course, you can't. Transportation cost is a constraint. I wasn't very clear in his models that he presented where that constraint comes into play, but that was his answer. Now, he works on interesting problems in cloud computing, for example. He told me he works on resource allocations for Amazon, and the resource there is often data, and that brings us back to Onur Mutlu, to Philip Wong. Okay, data-centric compute, data-centric cloud compute, all of these things are connected. The question here in the operations management space is, how much data do I store in how many edges do I have where data is stored, and how do I replicate that? It's expensive to have data stored everywhere. It's expensive to move data around. So I have to find an optimal solution for that type of problem, and that, of course, resonates with even Onur Mutlu's problems, which are not network-driven, let's say, a la Amazon. It's more the network within a computer. But again, it resonates. I looked a little bit what kind of different courses this professor is offering, and the courses is offering, I mean, basic, of course, operations management, management science, so things along those lines, and then more advanced topics, in particular, the problem of cloud computing, which he mentions in the paper, that cloud computing hasn't really been attacked by the operations research community. And I think the reason it hasn't been attacked is, I think, because the workloads were relatively simple, and now the workloads are getting more complex. And there you go. We have the operations research community now involved. I think operations research gets involved when there is scarce resources, and whether the resource is scarce in terms of constrained by transportation, whether it's scarce by location or data availability, whatever the scarcity of the resources, operations research comes in and solves it. I wonder whether this problem can be solved through reinforcement learning. In fact, at the CARS seminar that I attended on Thursday, I saw a group which solves a similar problem that this professor is trying to solve, which is resource allocation in sort of the last mile delivery space, and the problem that the cars people were solving is the problem of allocating ride shares for Lyft and Uber. But it's similar in a sense that you have a certain amount of vehicles, a certain amount of transportation capacity, which then can be allocated across a geography, and you have to think about network problems, queuing problems. And I think reinforcement learning is a way to deal with this. This goes back to even the talk that I attended about vehicle air vehicle coordination, drone vehicle coordination. So these are all very similar problems. We have a bunch of vehicles that need to go from A to B, that need to serve certain demand. How can we simultaneously have them all move around without hitting each other, without being also having spare capacity, without having too long wait times? So those are problems that operations research can attack, and I think it's very interesting to see that those problems are being attacked. An interesting seminar I attended was part of the humanities department, and Joe Fox was talking about the need to take humanities more seriously. And what I find interesting about the seminar is that questions came up that also come up in lots of robotics and AI seminars, which is, what does it mean to be human? What's the role of humanities? And I think she was talking about the crisis of humanities in the sense that nobody's taking humanities very seriously anymore. People can't get jobs, all that kind of stuff. And I said, I'm going to flip this on its head. I think there is a crisis in humanities in a sense that we have lots of thirst for knowledge about what it means to be human, what's a good novel, what is a fair model, all these kinds of things that AI researchers now are forced to answer because they're teaching the machines. So I was asked by people in the attendance what do I suggest as a technologist? I outed myself as a technologist. And what do I suggest they should be teaching students in the humanities? And I said, teach them how to teach machines. I think that's the low-hanging fruit right now, is how can we teach machines what it is to be human, what it means to summarize a novel. All these types of questions can be taught by humans to machines. I think there's a thirst for that. I think there are people at Berkeley that work on this type of problem. I think it's actually adjacent to the problem of annotation, right? How do you annotate, let's say, videos and pictures? I think it's a human problem. Like, we want to understand what we see. The machine wants to understand what it sees, but we want the machine to understand the same way we understand. And this is key, okay? This is where the humanities comes in. We want the machines to have an understanding of the environment which is equivalent to our understanding. Only this way we can actually align them with us, because no matter what we teach them afterwards, if they don't see the world the way we see the world, we're going to have a problem. And I hope that is part of Fei-Fei Li's book that she's presenting next week, where she just wrote a book, The World I See. And I hope that's part of it. Definitely, if you want to work on, let's say, fairness of AI, of accuracy, truth, any kind of stuff, you have to start with, okay, what is it I see? What is the perception? And do we agree that that is what it is? Crypto can help here also. How do we even agree how to annotate a picture, for example? How do we agree how to annotate an LLM model in terms of, is it a good model? Does it have a good representation of this particular novel? Is this particular representation of history correct? How do we do that? Is it right for people to have conspiracy theories? We have this normative inclination by academics all over the world to sort of look down on people and say, well, if you're a conspiracy theorist, that means you're anti-vax and you're a climate change denier. All these normative things, academia decides. Right now, academia decides what is and what isn't. And I think the humanities is part of academia. They're losing the track to others. I think in general, this is a much, much deeper question. And I think Joe Fox helped me crystallize that question. That's why I think this was the most important seminar of all the seminars I attended last week, because this is really what it's all about, right? You have to not just understand what is the world around us and teach the machines. You have to agree on making sure that what you think you understand is really what you understand. So again, what is the truth? And I think it just keeps going on and on. I think the Digital Economy Lab, the Human AI Center here at Stanford are beginnings of that. I think it's important to connect people. I think it's much, much more important to work on technologies of how to measure things. I think measurement is another one. So it's really, consensus and measurement. So we're going into crypto space here, actually, if you think about it. This is what crypto supposedly should be able to solve, according to Sergio Micali, excuse me, what is and what isn't. Decide what is and what isn't. It's one of the biggest powers. And I think the best way to deal with that is to have a consensus mechanism decide what that is. So again, this seminar was really, really important in that sense.
The last seminar I attended was the CARS Center, the Center for Automotive Research, Stanford, where the Chief Science Officer of the Department of Transportation was giving a keynote, and posters were presented about autonomous driving research, about new mobility research, electric mobility, and those sort of things. I want to mention three things I mentioned yesterday already. I think the mission creep of government is unfortunately visible in events like this. For example, the Department of Transportation person was talking about, having a more equitable transportation infrastructure, which is absurd. There was a paper presented that wants to somehow give credit to poor people so they can use a fast lane on a highway. Those are all, I would say, typical examples of mission creep. I'm not against giving people of underprivileged, origin more advantages to society, but you have to do it in the right place. You can't do it within the context of transportation. Transportation is an infrastructure project that needs to be built in terms of efficiency and economic cost and time and budget. That helps everybody, and then you can allocate resources in other venues so people can afford them. I also felt like the Stanford faculty was kissing the behind of this person, because you can see how academia and government are intertwined. Another, I would say, pretty negative thing. But nevertheless, it was an interesting venue as a whole. I appreciated the venue. I also appreciated the Department of Transportation actually doing a listening tour, inviting people. All of these things are fine. The paper presented in the poster session were, a couple of them were interesting. I think one where they use reinforcement learning for resource allocation in ride sharing. I think that's an interesting problem, similar to Peng Wei's problem with the collision avoidance of autonomous airborne vehicles. Here you have a similar problem. You have collision avoidance, but also resource allocation. For example, where should I go? Where should I pick up the next ride? Where should I charge? Those types of problems can be solved in sort of control theory context, as well as in a reinforcement learning context. The other really interesting paper, although, was from Sergio Pavone's group, and that was on using large language models to detect anomaly of data or out of distribution data. So this is really an important paper, because it tackles several massive issues of machine learning. One is, what is out of distribution data in the first place? How do you define that? And there's certainly some techniques to define out of distribution data. edge cases. We can call them edge cases also. The other is also annotation problems in the sense, okay, how do we even decide what is an edge case and how do we know? Now, what they do within the context of LLMs is they take a visual impression, so they take an image, translate it into text and use it as a prompt, and then have a large language model decide whether what the image sees is out of distribution or not. So this to me is, I think, an interesting idea and a method that could be used in, automated annotation. It could be used in automated labeling, for example. This paper definitely has some interesting legs. Here's just a quote from how they actually proceed. At some sampling frequency, the monitor examines the robot's visual observation and transforms them into textual descriptions. These scene descriptions are then integrated into an LLM prompt that aims to identify any factors that could give rise to a policy error, unsafe behavior, or task confusion. We emphasize that the level of task consistent specificity of the monitor is determined by the context provided in the prompt. So I think you definitely have some classifier issues here. You're translating pictures into prompts. This is what, let's say, Karpati, I think, did his PhD on. So this is definitely a difficult problem. Technology has advanced, and you can see how things are interrelated. Picture to text is important, but accuracy is important, and by the way, annotation also. I asked Amin, one of the authors, about annotation and the problem. He didn't even know what I was talking about. And this is part of the problem. I think people are really, really narrow in these fields, and there's a lack of sort of commonality, of creativity, of understanding cross-border problems from different areas, even within computer science. So it's really the siloing of academia is prevalent. You can see that, and it's unfortunate. It's not a good thing, but it is what it is, and that's part of this sabbatical, is to understand what's going on in academia, to understand what people are working on and what kind of people are working in this field. Lastly, I also want to mention wireless traffic signals, another interesting concept, I think. Obviously, the idea here would be that you don't rely on vision anymore and that autonomous robots could just sort of have traffic signals fed. The question here also comes up, well, do we even need traffic signals, right? Can we just use sort of vehicle-to-vehicle reinforcement learning type solutions, versus do we need central planning? I think these are pretty interesting questions. So to summarize, the week from 10:30 to 11:03, very, very interesting week. I'm very happy with the progress that I'm making. I've done a seminar on material science / computational computer architecture, device level, nano manufacturing. I mean, all these things were part of that PhD by the lady that was presenting from Georgia Tech. I've attended a seminar, and excuse me, the idea is to do sort of in-memory compute based on active oxides. Then I did a seminar, Peng Wei, about autonomous flight vehicle control and using reinforcement learning for vehicle-to-vehicle communication. I've done a seminar, chemical engineering, about autonomous biolabs and robotics and the use of robotics in bioengineering. I've done a seminar on the physics colloquium, which was probably the weakest seminar by Chris Laumann, just because he's not a good presenter, on quantum spin ice. Interesting problem. And I think what's really important about the quantum spin ice presentation is less what the results are. That is really for theoretical physicists to argue about. It is more to understand the work of a physicist who is at the cross of the border of theory and practice. I've done a lecture on astrophysics and the solar astrophysics, and the person
really well describe what the issues are and how important it is to predict space weather that comes from the sun. I've done a seminar on operations management and the idea of resource planning and flexibility. I've done a seminar on humanities futures. Joe Fox was talking about the crisis of humanities, which I think was very inspiring, because I think I'm connecting the crisis of humanities within the humanities with the crisis of humanities within AI, and it's a very different type of crisis. There's a lack of knowledge and thirst for knowledge about what does it mean to be human, what should we be teaching machines. And I think the bigger takeaway is that I think what humanities should be doing more and more is teach machines. And this is also an idea for a business, actually. How do we teach machines? That, to me, really important. I've done a seminar on sustainable mobility, the car seminar, which was really important, I think, in terms of understanding how the government works and how the interaction between government and academia, and then, of course, some of the papers, in particular the paper using LLMs and out of order distribution of data. Thank you.